there are also changes related to algorithms. There have been lots of ML algorithms before: linear regression, decision trees, genetic algorithms, support vector machines, just to name a few. One in particular has revolutionized machine learning recently: neural networks. But neural networks are not new. They have also been around since the 1970s. Neural networks mimic the way a human brain works. In our brains, we have layers of neurons feeding into other layers. But for complicated mathematical reasons, those deep layers of neurons didn't work in computing. So people used shallow neural networks, which weren't very powerful. But then came advances in what we call deep neural networks. Many advances were made by Geoff Hinton at the University of Toronto. He and his team of students got deep learning to finally work, with the help of many other researchers, of course. These deep neural networks are examples of deep learning, which propelled ML forward even further. One key advance was a special type of layer in a neural network called a convolutional neural network, or CNN. Think of a CNN as scanning an image, the way your eye scans a really large image to take in all its details. But you also see the image as a whole. Here, you see an image of the famous computer scientist and admiral, Grace Hopper, as the CNN detects all the horizontal edges in the image in order to see it better, like you and I do. CNNs work really, really well for images. They can perform image-related tasks with a very high level of accuracy. Unfortunately, CNNs need a lot of computing power. When they were originally developed, it was very expensive to use them. But a few years later, many technological advances made using CNNs more cost-effective. Distributed computing allowed large computing jobs to be split into manageable pieces. But distributed computing is subject to diminishing returns because there are network speed and reliability issues when computers have to talk to each other. GPUs, which are built as graphics cards for rendering in games, turn out to be really good at accelerating machine learning computations. Andrew Ng demonstrated in 2006 that GPUs function as ML accelerators. Training a model with a GPU was 70 times faster than using traditional computing hardware. And this helped too, but only for a while. Part of the problem was that ML models were becoming increasingly expensive to train. Between AlexNet, which started off the deep learning revolution, and neural architecture search, which powers Google's AutoML, the computational cost of training grew 100,000 times greater. In this chart, you see different ML models that were developed over time, showing their accuracy versus their cost. As our models got better, they also required more expensive computation. That's because when you have more layers in a deep learning model, you need more data, and your compute needs become more expensive. Now, let's go back to how Google uses ML for its business. At Google, most of our models have millions of parameters. Remember, the parameters are the parts of the ML models that we adjust to make better predictions. And all those millions of parameters require lots of computing power. What does that mean for Google's ML models? Here's an interesting back-of-the-envelope calculation by Jeff Dean, who leads Google's AI division. He realized years ago that if everybody wanted to use voice search on their phones and used it for only 3 minutes, we would need to double our computing power. Historically, problems like this could be addressed through Moore's Law. Moore's Law was a trend in computing hardware that described the rate at which computing power doubled. For years, computing power was growing so rapidly that you could simply wait for it to catch up to the size of your problem. But though computing was growing rapidly, even as recently as 8 years ago, in the past 3 years, growth has slowed dramatically as manufacturers run up against fundamental limits. Compute performance has hit a plateau. It turns out that one way out is to limit the power consumption of a chip. You can do that by building what are called application-specific chips, or ASICs. Google designed new types of hardware designed specifically for ML. The Tensor Processing Unit, or TPU, is specifically optimized for ML, and it has more memory and a faster processor. Google has been working on the TPU for several years and has made it available to other businesses like yours for really big and challenging ML problems. Because of all of this technology, new hardware, distributed computing, new algorithms, it became feasible for more businesses to use ML. But it still wasn't easy. Part of the problem was that few ML software frameworks were designed for industry-scale usage. If companies wanted to do ML, they would need the expertise to create their own frameworks, and that was a steep cost, especially because ML talent is still relatively rare. But over time, more and more ML frameworks are becoming available and are making it possible to use ML at high levels of abstraction. One such framework is TensorFlow, Google's open-source, production-ready, distributed ML framework. It's what we use internally to build, train, and serve models. It's among the most popular ML frameworks available. But even with frameworks like TensorFlow, implementing a custom model requires technical expertise. That's where cloud technology comes in. And that's part of the reason why we're teaching this course. Cloud technology makes it easier to adopt ML for businesses at many levels of ML expertise. For businesses that want to run ML models they already have in the cloud, but for whom the economics of owning the infrastructure doesn't make sense, there's infrastructure as a service, IaaS, where you rent, not buy. Additionally, TPUs scale linearly, so you can train faster by running on more cores, which is another benefit of the economics of the cloud. Businesses can also use the cloud as a platform for doing machine learning and let the service manage the renting of hardware. With platform as a service, businesses can get data labeling, model training, and model deployment as services. There are even services to train custom models for you and serve them so you can make predictions. Finally, there's software as a service, like Dialogflow, based on pre-trained ML models. There are also increasingly industry-specific ML models that you can purchase and train with your own data on the cloud. In most cases, we recommend that you use the cloud for ML. But you should also be aware of some situations where the cloud isn't recommended. For example, you might have a data locality requirement. Or you might actually want to have your ML model make predictions on a device. For example, when you run the ML model on a phone, or if you need the ML model to work offline. Running models locally cuts down on networking costs, but there is a limit to how powerful the ML models can be. A common paradigm is to run a fast but not great model locally, but use the cloud when a more accurate answer is needed. So remember, the cloud is recommended for most ML use cases. It also helps to alleviate some of the hassle associated with getting the software working locally. And it can't be difficult to provision the hardware and use it efficiently on premises. To see how easy ML can be using ML as a service and cloud technology, let's try it out. In this lab, you use the AutoML tool to train a custom model without writing any code.